Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series, which are delivered for the BSc Physical Sciences students who are doing the paper on applied electronics, and we are passing through the section on quantum mechanics, and we will have a series of lectures in this chapter. We started in the last lecture with the uncertainty principle, then we have to go through the postulates of wave mechanics, wave function and its interpretation and so on, and contents of this lecture are as follows: uncertainty principle, postulates of quantum mechanics, Schrodinger equation, wave function postulate, derivation of Schrodinger wave equation. And in the last lecture I told you about the uncertainty principle. The uncertainty principle, as all of you should be knowing now, it states that it is impossible to determine the position and momentum of microscopic particles, say an electron, simultaneously accurately. So, the accurate measurement of both the momentum and the position of the electron is impossible. This is an inevitable problem, and we have to go into the origin of the problem. What is the restriction, what is the inherent problem or inescapable problem which makes the two which could not be measured simultaneously. So, once again the uncertainty principle says that the delta x into delta p is the order of h cross. What is delta x? It is the uncertainty in the position measurement, and delta p, p is momentum, is the uncertainty in the momentum measurement. As I told you in the last lecture, in classical mechanics you can measure both these things simultaneously and accurately. As I told you in the last lecture again, if a train is passing through a station, an express train, and when it crosses a lamp post, it is a lamp post that is the position. When it crosses, the momentum of the train can be measured, and the position, you know, it is a lamp post. Both of them can be determined simultaneously. But on the other hand, when you go to the case of electron, proton, neutron, such other microscopic particles, this indeterminacy or uncertainty comes into the picture, which says that the position and momentum cannot be determined accurately, what simultaneously and accurately they cannot be determined. If you try at the maximum, the uncertainty in delta x multiplied by delta p will be order of the Planck's constant, and if you want to determine one of them accurately, suppose I want to measure the position of the electron accurately, then what will happen to delta p? What is delta p? It is inaccuracy in the momentum measurement. If we make delta x is 0, what is delta p? Delta p will become h cross by 2 by delta x. Delta p will be equal to h cross by 2, delta x will go to the other side. If delta x becomes 0, that means you are trying to accurately position the electron, you want to determine the position of the electron accurately, then delta x should be 0. That means delta p will be infinity, because your delta x that comes in the denominator is 0. Therefore, delta p, the uncertainty in the momentum measurement will be infinity. So, if one of them could be determined accurately, the inaccuracy involved in the other one will become infinity. So, similarly, the energy time uncertainty. The inherent problem is, as I told you in the last lecture, I also mentioned about Rayleigh's criterion for resolution. If you want to see the electron, I want to see the electron, I have the electron here. If you want to see the pin using a microscope, you keep the pin at the origin at 0 0 0, you keep the pin here at the origin, and the coordinates are x is 0, y is 0. You shine the pin by ordinary light, you can see the pin at the crosswire, the pin is seen at x equals 0, y equals 0, that is the two crosswires are found and the pin is kept here. So, at the crosswire, at the intersection of the crosswire, the pin is positioned, pin is sitting there. So, your the position of the pin will be x is 0, y is 0, that is or a point you have at the intersection, the point is the coordinates are x is 0, y is 0. Now, when you go to a case of electron, you have the electron here, you want to measure its position as well as the momentum. How will you see the electron? How will you observe the electron? If you want to observe the electron, first of all you should know the size of the electron. I told you in the last lecture, you all know by now how much is the size of the hydrogen atom, what is the size of the electron. The size of the electron or the radius of the electron is of the order of 10 to the power of minus 15 of a meter. Where do you find 10 to the minus 15 of a meter? That corresponds to the gamma radiation. So, you have to make use of high energy gamma photon to see the electron. So, the electron is so small, because it is so small you cannot use the ordinary light to see the electron. I cannot see the electron, right. I have the electron here. You know, in the human system, human body, here in the whole room you have got hydrogen and oxygen atoms, you have got air, water vapor and so on, air molecules are there. So, you have atoms, electrons are found here. The electrons cannot be seen by the human eye. To see the electron, you have to make use of high energy photon. So, if the high energy photon is incident on the electron, what happens? It is as Vladimir Rednik beautifully states, the incident photon interacting with the electron, it is something like a bullet train, a high energy. You have a train colliding with a baby cart on the on the railway track, you got a baby cart, you got a plastic cart. The train is moving at a faster pace. What will happen? The train will be hitting the baby cart and the baby cart will be thrown out of the picture, thrown out of the railway track. Similarly, here if the high energy photon is incident, it will not allow the electron to sit at the position which it has been occupying, which you want to see. What will happen is the electron will be scattered, right. The collision is so violent. In the case of pin, the pin can be seen, the pin is not disturbed by ordinary light. You can see the pin either by naked eye or by using the microscope, pin can be magnified and seen. But on the other hand, when you want to see the electron, you have to use you have to necessarily use the inescapable problem. It is a inherent problem which one comes across when you want to see an electron. So, the high energy photon will violently interact with the measuring system, with the electron, and the electron will be thrown out of the picture. It will not be seen in the microscope. You want to see the electron in the microscope, but the electron will not be found in the seen in the microscope, in the vicinity, you cannot see the electron at all, because the high energy photon will throw the electron. So, therefore, there is a inherent problem, inescapable problem that you come across, that makes the things difficult, that gives you the uncertainty principle. That means, the delta x into delta p is the order of h cross. That means, you want to measure the position accurately, the inaccuracy in the momentum will become infinity, and lot of this is given by Wolfgang Pauli, and lot of expressions, lot of derivations have been made, and in the book written by Max Born, he gives different results, maybe delta x into delta p is either h cross or h cross by 2 or h cross by 4 and so on. The thing is so small which cannot be verified, but it is there. Let me now pass on to the postulates of quantum mechanics. I told you the last lecture the differences between classical mechanics and quantum mechanics, or Newtonian dynamics and quantum mechanics. The classical mechanics holds good for cricket ball, football, volleyball and so on, many whatever I am having in hand. For these things, the classical mechanics holds good. For a moving body, the train or aeroplane, the classical mechanics holds good, the Newtonian dynamics works. But on the other hand, when you are dealing with microscopic entities, microscopic particles like electrons, protons and so on, then the age old classical mechanics which was given by Newton or Galileo and so many people who have been responsible for the development of the classical mechanics, they are to be discarded. They will not, cannot be used for electrons. Electrons are responsible for the flow of current in your cell phone. The electrons are responsible for the light that is coming from the mercury vapor lamp that you have in this room. So, when you are dealing with the electrons, you cannot, because of the age old classical mechanics, you have to go to what is called quantum theory, which was given by Max Planck in the year 1901, and we are going to see in this lecture the equation which is derived by Schrodinger. It is called the Schrodinger's wave equation, which is the quantum analog of the famous equation F is equal to ma given by whom? Isaac Newton. You have all studied the Newton's second law of motion, from where you arrive at the equation F is force is equal to mass into acceleration. That is perfectly valid for classical objects. When you go to quantum mechanical objects, you have to replace the classical equation by an analogous equation, which is the so called Schrodinger wave equation. Before we derive or arrive at the Schrodinger equation, let me now summarize the postulates of quantum mechanics. The postulate 1 states the state of quantum mechanical system. By a quantum mechanical system, what I mean is a collection of electrons or a collection of protons is completely specified by a function. So, the state of a quantum mechanical system is specified by a function psi, which is a function of r and t. What is r? Supposing I am referring to an electron. So, r refers to the position coordinates and t denotes the time. At a given time t, what is the position of the electron? This I will be calling as wave function later. So, psi of r t refers to the wave function, or this function is called the wave function or state function. It has the important property psi star or t multiplied by psi of r t d tau is the probability that a particle is found at a point r and at a given time t. So, the complex conjugate psi of psi, that is psi star r of t multiplied by psi of r t, it gives what is called a probability density. The one that you have here psi of r t is called a probability amplitude, and the second one psi star psi gives the probability of finding a particle at a given point or and at a given time t. Okay. That is very important. Let us have a break at this point. Welcome back to the break. We are now passing through the postulates on which the quantum mechanics has been built on. So, the first postulate says about the wave function or the probability amplitude, and the square of which, if it is real, you can take the square. It sometimes psi may be complex, therefore, you take the complex conjugate multiplied by the wave function psi, that gives the probability density, is called the probability density in a given volume. It is a d tau is a volume element, right. So, it gives the probability. The wave function must satisfy certain mathematical conditions because of its probabilistic nature. For the case of a single particle, the probability of finding it is equal to 1. You got 1 electron in the case of hydrogen atom, then therefore, the probability should be equal to 1. The probability of finding the electron should be equal to 1. The wave function must also be single valued, finite and continuous. Single valued means at a given point it should have only one value. It should be continuous, that means d psi by dx should be, psi should be continuous, means what does it mean? If you have got psi 1 here and psi 2 here, at a given point psi 1 should be equal to psi 2. You have psi 1 should be equal to psi 2 in spite of the fact there may be a potential discontinuity. In certain specific problems which I will go through in the time to come, you will understand what I mean by continuity of the wave function, and it should be finite, it should not be infinity. You cannot say the electron has got infinite probability. Infinity can come only in mathematics and not in physics. Even if you take the energy of the universe or the temperature of sun, the temperature of sun or the energy possessed by the sun or energy possessed by the entire universe, they are all finite, right. You cannot the infinite universe, but the thing should be finite, and so it should be finite and continuous and single valued and so on. The postulate 2, it says to every observable in classical mechanics. What is observable? Observable is a thing that can be measured in the laboratory. What are the things which can be measured in the laboratory? I used a classical ball in the last lecture. A ball is running, it has got a finite kinetic energy. If a cricket ball is crossing the boundary line, it is moving with a definite momentum or definite velocity, right. Sixer means again the cricket ball is moving with a greater velocity. So, the velocity is a measurable quantity, the momentum is measurable, energy is measurable, they are called the observables, they can be observed, they can be experimentally measured. To every observable in classical mechanics, there corresponds to an operator, a Hermitian operator in quantum mechanics. So, in quantum mechanics, the observables that you had in classical mechanics are replaced by the corresponding operators. The postulate 3 says in any measurement of the observable associated with the operator, this operator, the operator A operating on the wave function psi should give you A multiplied by psi, and this A is called the eigenvalue, is called eigenvalue, and this is called the eigenfunction. Psi is called the eigenfunction or the wave function, and so an operator H operating on psi will be equal to E into psi. That is the so called Schrodinger equation. H is the Hamiltonian. Hamiltonian operating on psi will give you E into psi. E is the energy of the particle, energy of the electron or proton, whatever we think. H operating on psi will be equal to E operating on psi, okay. Something like that. So, to start with, you have an operator A operating on a wave function psi will give you small a times psi. This small a that you have got is an observable. It can be the magnetic moment or momentum of the electron or energy of the electron, which is an observable. Its eigenvalue is a measurable quantity. I will not comment about eigenfunction for the present, but eigenvalue is a thing which can be measured in the laboratory. It is observable, which can be measured in the laboratory. Okay. The postulate 4 states, if a system is in a state described by a normalized wave function, then the average value observable corresponding to it is given by the average expectation value E is given by psi star r multiplied by the operator E, again multiplied by the wave function psi of r, that gives the average value or the expectation, right. The expectation or the average value of this E is obtained by this particular expression, and the postulate 5 shows the time dependence come here, t comes here. It is the wave function or state function system evolves in time according to the time dependent Schrodinger equation. This equation that you have here is called a time dependent Schrodinger equation. What is H? H is called a Hamiltonian. What is Hamiltonian? In quantum mechanics, Hamiltonian is nothing but the sum of T and V. What are T and V? T is the kinetic energy and V is the potential energy. The kinetic energy of the electron plus the potential energy of the electron, T plus V is the Hamiltonian. So, the Hamiltonian operating on the wave function will be I h cross. H is the Planck's constant, h cross is nothing but h by 2 pi dou psi by dou t. T comes here explicitly, that is the Schrodinger's time dependent equation. The last postulate 6 states that the total wave function must be antisymmetric with respect to the interchange of all coordinates of one fermion with that of another. Electron spin must be included in this set of coordinates. Now, this is nothing but the quantum mechanical way of explaining or expressing the Pauli exclusion principle. In the previous lectures, I gave the Pauli, or I discussed the Pauli principle, the exclusion principle in detail using the quantum numbers n, l, m l, m s in the vector atom model. In the vector atom model, you come across many quantum numbers, as many as 7 quantum numbers. I discussed the Pauli principle and the use of the Pauli exclusion principle in finding the number of electrons you can have in the K shell, L shell, or in general in describing the electronic configuration of different atoms. Hydrogen atom has got only 1 electron, it will be first shell. Lithium has got 3 electrons, 2 will go to the first shell and the third one will go to the second shell. And you may ask the question, why can't you have all the 3 electrons in the first shell itself? The answer comes from the Pauli principle. The Pauli exclusion principle states that no 2 electrons can have the same set of quantum numbers. That is what I have stated using the vector atom model, in the case of vector atom model. But the quantum mechanical description of the Pauli principle is the following. It comes via the postulate 6. What is the postulate? Let me restate the postulate. In any fermionic system dealing with fermions, what are fermions? The spin half particles like electrons, protons. So, when you are dealing with particles having spin half, they are called the fermions. The wave function that describes a fermionic system should be antisymmetric in nature. What do you mean by antisymmetric in nature? When you interchange into electrons, you take 2 electrons, right, you have got an n electron system. you interchange, you take the hydrogen molecule, you got how many electrons you will be having, what is hydrogen molecule, combination of 2 hydrogen atoms. So, you got 2 electrons, when you interchange you got 1 electron here, another one here, when you interchange the 2 electrons you should get the wave function with a same wave function, but with a negative sign, that is called the antisymmetric nature. If you are getting with a positive sign, that is a symmetric wave function, but when you are dealing with electrons, the wave function should be having the antisymmetric property, that is the postulate number 6. That is the the way in which you explain the Pauli principle, the quantum mechanical description of the Pauli exclusion principle, which I have already stated, and we have made use of that in the configuration of electrons in atoms. How do you keep electrons in the K shell, L shell, and how do you give the electronic configuration, the arrangement of electrons in the periodic table. Okay. Those things we have seen, where we have made use of the Pauli principle. This is a restatement of the Pauli principle. It is a more rigorous manner in which the Pauli principle is explained once again, right. Some important observables. What are observables? The things which can be measured in the laboratory, such as position, momentum, kinetic energy, potential energy, total energy, angular momentum. These are some of the observables. By observable, as I told you, they are nothing but things which can be measured in the laboratory, and they are given this kind of symbols, right. In classical mechanics, you give the position R, momentum P, kinetic energy is T. I told you in the Hamiltonian, what is Hamiltonian? The sum of the kinetic energy plus the potential energy, T plus V. This is what I stated bit earlier, that gives the total energy. Okay. The angular momentum Lx, Ly, Lz. The operator symbol is the same that you have got here. You have a cap here above the symbol, that is the operator. So, you have now the momentum operator is minus I h cross multiplied by I into dou by dou x. For the momentum of the electron in a x direction, the other components will be missing. So, let us simplify the thing. I will write p x. P x will be minus I h cross into I into dou by dou x. Similarly, the kinetic energy along the x direction will be minus h cross to the power of 2 by 2 m into dou square by dou x square. The potential energy simply multiplied by V of r. The total energy will be the sum of the kinetic energy, you got the entire thing plus the potential energy. The angular momentum will be along the x direction, you see Lx here, right. Along the x direction will be minus I h cross y into dou by dou z minus z into dou by dou I. That gives the angular momentum of the electron, of the particle in question along the s direction. Similarly, other components that they have got along y and z directions are given as Ly and Lz. Okay. The person who revolutionized our understanding with regard to electrons, but for the Schrodinger wave equation, we will not be able to explain or understand the working of your cell phone. What is cell phone? You have got electrons, the electric current. What is electric current? Is nothing but the flow of electrons. So, the understanding of electrons, right, the proper understanding of electrons, they are microscopic particles. So, the fundamental equation which is to be used for electrons was given by Schrodinger. It is known as the Schrodinger's equation, Erwin Schrodinger, the details of which we will see in the next lecture. And now we will pass on to the summary of this lecture. The inherent problem in measuring both the position and momentum simultaneously and accurately should be understood. Schrodinger equation is the quantum analog of Newton's famous equation F is equal to m e. The above equation can be obtained simply by introducing the de Broglie equation for the wavelength which is seen in classical wave equation. The inputs which go into the Schrodinger's wave equation is the potential energy V, and you have to impose what are called boundary conditions for solving any problem in quantum mechanics. The questions that we have before us are: what is the inherent problem in observing the electron? State the postulates of quantum mechanics, give the Schrodinger equation, mention the input in the Schrodinger wave equation. Can you determine the eigenvalue and eigenfunction and verify them experimentally? With this we come to the end of this lecture, and the rest of the things we will see in the lectures to come. Thank you.